Right, good morning everyone. Thank you for joining us and welcome to the 5th Tiger supply chain webinar. The theme for today is reliability and condition monitoring of tidal turbines. So thank you very much for joining us. I'm just going to do a little bit of housekeeping very briefly. Firstly, I'd like to say thank you very much to Oceans Gate Plymouth for co-hosting this webinar through the Marine Technology webinar series. You may have noticed through the registration process that they have regular marine technology webinars on a Wednesday. So definitely something to keep an eye on there with some really interesting topics. This webinar will be recorded and we'll make it available on the Tiger website after the live event. So if you have to cut short or anything, you will be able to retrieve both the slides from each of our speakers as well as the live recording. We have a Q&A session planned for the end of the webinar. So once we've had all 4 of our speakers, we'll have a session there where attendees can ask questions to our speakers. Anyone can post a question and you can also upvote it if you haven't posted it, but you're interested to hear the answer to that question. Feel free to give it the thumbs up and that will bump it up the queue and give us an indication that more people are interested to hear the outcome for that question. And if you're having any technical issues, please use the chat function rather than the Q&A. And we've got someone on the background there too to support you with any issues. So just a quick run through the agenda. So I'll do the welcome and introduction, give an overview to the Tiger project. I then hand over to my colleague Hyunju, based up in Blythe, who'll run through his pitch system health monitoring and machine learning project. He'll then hand over to Fraser, who'll give us an insight into some of the early challenges of operating a first-of-class machine and the opportunities there for supply chain. Then Mikhail from HydroQuest will also give us some insight into the reliability from design of their OceanQuest device. And finally, then Stephen Robertson will give us an overview of the ORE catapult test facilities that we have available, not only to Tiger partners, but also to supply chain. And as I mentioned previously, we've got the Q&A session lined up at the end. So please do, if you have any questions throughout the webinar, post your questions on the Q&A function. So very briefly, what is Tiger? So the acronym Tiger stands for Tidal Stream Industry Energizer Project. It's a 45.4 million euro project, of which just under 30 million euros is ERDF grant funding. It's a 4-year project, which kicked off in July last year. And we're funded through the Interreg France Channel Manche England programme. It's actually Interreg's largest ever funded project, and it's a collaborative cross-border project with the UK and France. So this just gives an indication of the numerous partners we have on board with Tiger. We have a mixture of both technology and site developers, academic partners through the 6 universities, and we have 2 regional agencies as well to support us with reaching out to supply chain and SMEs. You can see on screen, so the dark green shaded area is actually the Interreg channel program area, where ideally the majority of grant funding should be spent. So in essence, that's where all of our projects are based, bar Ramsey Sound, which we've had special permission to include in the project, albeit sitting outside of that area. We have a number of project partners who are also based outside of area. So that includes EMEC, the European Marine Energy Centre, based in Orkney, Orbital Marine Power, and QED, who are both based up in Scotland, and Manchester University. And we also have Senio, who is the caretaker for the Pampol Brehat test site. You can see just here off the coast of Brittany, and Monesto, who are a Swedish company. So we have a really strong mixture of partners on the project and quite a lot of activity. The Offshore Renewable Energy Catapult is the lead partner on Tiger, so we have sort of overall responsibility for delivering the Tiger project. And on this slide, you can see slightly more clearly the development sites within Tiger. So we have Ramsey Sound, as I've just mentioned, off the Pembrokeshire coast in Wales, sitting outside of the funding area. Here they will retrieve the Delta Stream tidal turbine, which was installed back in December 2015, and redeploy a new turbine. We have the PTEC site, which has been in hibernation, but I don't know if recently you've seen the news that EMEC are now going to support the PTEC project and bring that alive again, reactivate the site and renew the consents there, which is very exciting news for the tidal sector. We have the Ras Blanchard tidal site, which is the world's second largest tidal resource. We have both HydroQuest and Normandy Hydrolien, which is a joint venture between CIMEC Atlantis and AD Normandy, both seeking to consent the next generation commercial arrays. We have the Pampol Brehat test site, where we currently have the HydroQuest 1 megawatt Ocean Quest device installed and operating and doing various tests. And we also have plans to install Monesto's next generation tidal kite at the test site in 2022. And finally, the Morbihan Gulf site, where Sabella will be installing 2 of its D08 turbines, so 250 kilowatt turbines in various, in 2 slightly different configurations. So quite an interesting project from a design perspective. And we should get some really interesting insight from that. So the Catapult, as I've mentioned, is the lead partner. I'm based down in Hale, actually working from home currently, just on the south coast there, but not far away. Yeah. So what is Tiger about? So the Catapult did a cost reduction pathway report back in 2018, which was looking to establish, what the levelized cost of energy is for tidal stream technology. So back then we had approximately 10 megawatts of installed capacity around the UK, and the average cost of that was about £300 per megawatt hour. Tiger's focus then is, how are we going to bring that cost down? So we have this prediction here of by 200 megawatts of installed capacity will be below the £150 per megawatt hour, and by 1 gigawatts worth of installed capacity below the £100, and competitive with nuclear power, for instance. So Tiger's focus is on these green blocks. So initial accelerated reductions. So this is where economies of volume, economies of scale, and accelerated learning come into play. And through Tiger, and in particular sort of the Ras Blanchard commercial array consenting process, and the design of the next generation technologies, which are predominantly getting larger. Tiger will tackle some of the initial accelerated cost reductions. The learning by doing, so we've seen the suite of projects contained within Tiger, and the various optimized processes that we're looking into for the various projects. And obviously installing and operating a device, you're going to make learnings and understand how to do things better. And ultimately that should lead to better investor confidence in the technology. They've seen it installed and how it performs, and therefore the cost of capital and the risk associated with those projects will come down. So that's how Tiger will sort of tackle those particular areas that we need to look at in order to get the levelized cost of energy for tidal stream in a downward trajectory. So how will we do this? So you've seen the suite of partners we have and the expertise there, and sort of the ethos of Tiger is that we're looking for partners to collaborate and share the knowledge and learning that they all achieve throughout Tiger and previously. So work package 1 is all about development projects and the activities contained within those. Work package 2 is all about sector and technology development. So really looking at systems, components and processes, and looking to innovate and work very closely with supply chain partners in doing so. And work package 3 is effectively our opportunity to summarize and to collate all of the information from those first 2 work packages and really show and shout about how tidal streams costs will come down and how we can be part of the green recovery. So supply chain engagement activities are a critical part to Tiger. And one of the physical outputs from Tiger is we need to deliver 40 different equipment design specifications. And we really need to work with supply chain to do that. So we have numerous partners working on various different design aspects, and they will undoubtedly need to procure certain services. And so it's key that we're able to advertise and talk about what is required from Tidal. And that's, so the first series, this is the fifth of series 1 webinar. And this was really sort of a shop window to shout about the Tiger project and just to get supply chain up to speed with what Tiger's about and what we intend to be doing over the next 2 to 3 years. So Tiger welcomes the opportunity to collaborate with other like-minded projects, associations. We're keen to hear from as many supply chain companies as possible. So if you are interested and you have an idea, or you just want to have a discussion about the tidal sector in general, please do get in touch. And here's the contact details for us at the Tiger project. So yeah, please do get in touch if you would like to do so. Okay, I'd like to hand over now to the first speaker. So my colleague Hyunju Lee for the first speaking slot. So over to you, Hyunju. Okay, Hyunju, I think you're just on mute, that's all.
Good morning, everyone. Can you hear me? And can you see my screen now?
Yeah, perfect.
Okay, great.
Thanks,
yeah. Thank you, everyone, for your attending this section. I'm Hyunju Lee, working for Oali Katapult as a leader of drivetrain knowledge area to improve the reliability of drivetrain of offshore renewable energy. Today, I hope to share what we've achieved in the area of pitch system test monitoring with machine learning algorithm for offshore wind turbine. In this presentation, I showed our approach to identify the bearing issue, and result will be presented. So, what is the problem? According to this pie chart in right side from Wind Europe ORG, the pitch system failure accounts for most downtime and has a highest rate. Because of the increased blade inertia and increased maintenance cost, pitch failure will be more critical on large offshore wind. But when we start this project, there are actually no effective detection method for whole pitch system, except the SCADA system, which provide only low frequency measurement data on some number of components inside of the pitch system. Based on this understanding, we aim to develop a health monitoring method for pitch system with existing SCADA data, which will require no extra hardware and will generate automatic warning and alarm signal in advance. As a result, with this system, we hope to reduce the number of unplanned maintenance for pitch system. To achieve our goal, we use both of the data from simulation and field measurement. Especially for the field measurement data, we use this 7 megawatt wind turbine, which located and operating at Levenworth in Scotland. This turbine switches on and off the individual pitch controller, which called the IPC, according to the wind condition. And this internal turbine controller has been improved several times after it started to operate. operating condition for pitch bearing is very hostile. For example, very high bending moment from large wind blade with low speed oscillating or standstill still condition happen very frequently. In the offshore wind, individual pitch controller is becoming more common to reduce the load on the turbine structure itself, but this individual pitch controller can increase the small amplitude oscillation in the pitch system. And this small amplitude oscillation can increase the and accelerate the raceway fatigue or force prevailing in the pitch bearing. We focus to identify how many these small amplitude oscillation can be observed in real field, and to check if the real field operation is similar to the simulation result during the design stage or not. So our basic approach is that when we design and develop a wind turbine, we selected the bearing for pitch system based on design calculation. But we don't know yet how accurate that design simulation result is. So we hope to check and compare directly the same operating condition, the number of cycle on simulation to the number of cycle on the actual measurement. To compare field data with the simulated result, we developed a cycle counting tool with the suggest core algorithm, including the beam counting and range pair counting method. And also, after we count the number of oscillation for both of the real field and simulated data, we use the Harris method to calculate the bearing fatigue life. So in detail, we use this the beam approach based on the wind speed. The occurrence of 10-minute average wind speed was recorded from Levermoss development turbine operation, and total 36 data set we have been investigated, and this 36 data set can cover whole range of normal power production. And also we use the bearing reference life with the modification factor of 1, and we only use the MX and MY loading condition in bearing because that is the major contributory load component. And also 1 year SCADA data on the normal power production was investigated. The whole 1 year data was acquired, and especially the 1 meter per second step wind speed beam, and 3 SCADA data set for each of wind speed beam investigated. And also we ignore the very small variation of pitch position less than 0.05 degree. So we consider this less than 0.05 degree of movement as a stationary condition for bearing. And especially for this study, we investigated double low 4-point contact ball bearing. Approximately, the size of the bearing is 4.4 meter in diameter. So this chart shows the correlation between the measurement and the simulation. So as you can see, the blue line is the actual measurement data, and the yellow line is the simulated data. So in the industry, we normally use the very well-known commercial program like a bladed or fast to calculate load on the wind turbine system. And one of the evaluation methods is just to compare the simulation result of wind speed and the power output. So as you can see, if you can see this level of correlation between the simulation and measurement, then you can assume the load also can be acceptable level from simulation. But that is a normal practice. But what we found is that even though the load and the wind speed and the power output result from the simulation is very in line with the actual measurement. What we found in the actual movement in the pitch system is something like this. So this is our fatigue calculation result here based on SCADA data, the measurement data. So during 1 year operation, actually the 2017, accumulated pitch bearing fatigue damage accounted as a 3.3% based on L10 life calculation. Actually, that is far less than the simulated result. So in the design stage, the simulation result show the fatigue damage from 1 year, exactly same year's operation, can be up to 32.6%. It's 10 times more damaged than actual SCADA data set. So even though the wind speed simulation and the power output simulation is very similar to the actual movement, the actual fatigue damage on the specific component can be very different from the simulation result. So why? As you can see, the simulation tool, commercial tools normally accept a very conservative approach to prevent any the catastrophic failure in the field. So as a result, the simulated load is actually the 1.5 times higher than the measurement data. And this is the comparison between edge-wide moment from the SCADA, the measurement, and also from the simulation. So blue line is the measurement, and the orange line is the simulation. You can see the very similar trend, and also sometimes in engineering world we can accept this level of difference, but this small difference make 10 times different, make a 10 times smaller fatigue damage in pitch bearing component. It's the same as in the flat ice movement also. As you can see, the trend itself is very similar. So in the design stage, we can say that in engineering world, this level can be acceptable, but still the result can make 10 times different. And also the total number of cycle also a little bit different. From the measurement data, most frequent amplitude shifted toward a far smaller range. Even though in the industry, we normally use the two different type of pitch control. One is the individual pitch control to reduce the structural load, and the other one is the collective pitch control. That is to move all three pitch control together in same position. So this level-most turbine use the both of pitch control based on the wind speed and the operating condition. So we can find very similar and actually the quite good level of accuracy of calculated or simulated pitch movement on the collective pitch control algorithm. But in the individual pitch control algorithm, the actual cycle count is totally different in the simulation. So as you can see, the blue and yellow line and the green line indicate the pitch movement on the individual pitch control algorithm, the actual the measurement data, and the yellow line is the simulated pitch movement. So even though the trend itself is very well in line with measurement, the actual amplitude can differ quite a lot. So why? We identified this turbine controller has been tuned quite a lot of time from prototype commissioning. So individual pitch control amplitude factor was introduced to tune the individual pitch controller inside of the turbine. And this introduced the individual pitch control amplitude factor is not applied to the bladed simulation model, which lead to the major difference in the individual pitch control behavior. As you can see, this yellow, the blue line and on the red line is average motor current. So to prevent the overheat problem in the pitch control motor, they introduced this IPC amplitude factor. So when the motor current reaching up the threshold level, then they deactivate the individual pitch controller. And to develop the predictive health monitoring system for this position, we filter the SCADA data to generate normal and fine operating data, and use this fine data set. We trained the machine learning algorithm. So now this algorithm can predict the value of target signal under normal condition with more than 90% of accuracy. And when the measured value is different from the predictive value, this algorithm starts to generate warning or alarm. If this difference continue or increase for predefined time period, this algorithm will require the maintenance of the pitch system. So I hope to share this case study, which can show the evaluation result with a simulated data set during the design stage can be largely deviated from what with the measured data set. With lower measured moment load resulting in much less fatigue damage for actual turbine. However, increasing the portion of possible wear missing. So what is the lesson learned from this wind industry for tidal developer? I think the tidal turbine will start to adopt this pitch control algorithm to increase the size of individual tidal turbine. And in the industry also, when the size of the turbine start to become bigger than 1 megawatt, the OEMs actively adopt this pitch control system. But actually, the design assumption and simulation and calculation can be hugely different from what actual operating, what is actual measured in the field. So that kind of calculation should be evaluated during field commissioning. And to evaluate this design assumption and simulation result, number of loading cycle should be measured. And also, with the state-of-art design data processing technology, the early stage fault can be detected by using basic SCADA system. Okay, I think that is the end of my presentation. Thank you for your attention. Do you have any question?
Thanks, Hyunju. I think what we'll do is we'll move on to Fraser next, and we'll answer any questions at the Q&A session at the end. So if anyone has any questions for Hyunju, please do put them in the Q&A.
Okay, thank you. So then now it's time to introduce Mr. Fraser Johnson, Main Operation and Maintenance Manager, to present the experience of the early life operation of the 6 megawatt Pathfinder array. Thank you.
There we go. That should be better. Good morning to you all. Sorry, split between two screens. So yeah, going to take you through the Maygen project, some of the early stage operations that we've undertaken, a bit of history around what we've been doing, and then some of the work we've been doing on condition monitoring and understanding the assets that we've currently got on site. So the Maygen project, it's a 6 megawatt array. The second array to be built, the first was by Nova Innovation up in the Shetlands. Theirs was just under a megawatt. This is 4 turbines, 1.5 megawatt a unit, so 6 megawatt array. 3 Hammerfest turbines, what we call 1, 2, and 3. And then the 4th turbine is the AR 1500 from Atlantis, which recently had a subsea hub installed under the Saltire project. Converters are onshore, so subsea cables, 1 from each turbine, this being first of class. Didn't want to get into clusters of turbines, so individual export cable. The converters and the transformers are all onshore, and then we've got power control and protection into the local 33 kV grid up at the top of Scotland. So the location, we're in between the island of Stroma and the Scottish mainland. Just to the right of that picture is John O'Groats. And as the tide flows through the Pentland Firth, it goes through the main channel, or it squeezes through the inner sound, and that's where we pick up the flow. So the Maygen site's consented for 60 turbines, 86 megawatts in a phased installation. 4 turbines in so far, and then looking for future expansion. Just a quick one on the dates. So the project really started 10 years ago now, October 2010, with the Crown Estate leasing agreements. Construction started 2014, 4 years of construction. And then what we class moving into the operations phase in April 2018, and have been there firmly ever since. So the array was really set up, designed and developed looking at the future expansion. So using the equipment that we would expect to use on large arrays. So DP jackups for the foundations, jackups for the foundations, and DP vessels for the turbines. Typically the turbines are between 150 and 200 tons. The foundations they're about 1,400 tons of steel sat on the seabed. To date, 34 gigawatt hours of production to the grid and climbing, thankfully. And we've put in about 82,000 operating hours onto the turbines that we've got. So looking at data, with this being certainly the first of class, first of series, call it what you wish, there's a lot of information being generated. So unlike, say, maybe typical wind turbines that take their SCADA data and then process it for a 10-minute average, currently everything that we collect is 2 hertz, and we have a very large historian bank across the two as being competitors. It does make some challenges on the data control, the data side. So we're looking at the turbines themselves, ADCPs, we've got SKF vibration monitoring throughout both turbines. But we're talking here about turbines, but I must admit, Maygen, we talk about arrays. So we start talking about the converter, that being, in our case, separate to the turbine. So it's a separate system. We have HV protection and distribution, which again is part of the turbine array system and can impact availability. So again, we look at that. And we also look at the grid, G59, G99, and all the activities we have to work with an onshore wind and substation, onshore weather station and substations, so we know really what the operational conditions are outside, and if that has any effect and impact on the operation of the kit. So looking at the array monitoring, what do we monitor and why? When the turbines were first installed, the turbine suppliers were very focused on construction, get the construction contract done, get it installed and get it operating. And there were some expectations around array monitoring and how we would monitor and what we would monitor. Most of them have come to bear, but some of them really haven't, and experience of operations really changed that. So we kind of have three main areas. One is revenue generation. So it's a commercial project. We have debt to finance. So understanding what our generation actually is against the backdrop of a forecast is very valuable to us. It's something that we have to understand. And being a first of class and being an early stage, we don't have a huge amount of information on power curves these turbines are going to generate, and understanding the conditions, which I'll come back to, around the flow, which is one of the areas where we've seen some of the biggest variations, I suppose, of the tidal flow is very different to wind, which may be a significant difference between us and more traditional offshore wind floating and fixed systems. Maintenance, preventative maintenance cycles, looking at that planned and unplanned. A little bit early life, I must admit, for that. So talking about conventional planned maintenance for a first of class unit that hasn't yet done a maintenance cycle is a little bit too early, but it's something that we are working and setting ourselves up for. And then asset integrity and risk management. We've had a lot of work in the last couple of years with underwriters and insurers. That market right now is quite difficult, very challenging to be around and be involved. And offshore wind has had some significant effects on that, that we're feeling the effects of and then trying to manage. We are different to offshore wind, but it's something that the underwriters don't fully understand and don't appreciate. So it's something that we are working very heavily on for the economics for the future. Looking at some of the activities we have and how we've approached this with the phases of, say, condition monitoring. We've reached out to a number of external consultancies, and we've had people come and approach us, and we don't yet have enough information really to pull together. Don't have the number of turbines, number of hours to really pull together this predictive maintenance machine learning. So one of the areas we are looking at is normality modeling. These couple of slides came from a company called Jungle. We've been doing some work with, had some conversations with, and it's really that normality modeling of what is normal. And over the first 6 to 9 months of operation, we would get information from the turbines, and it would then take a very long time to understand, well, is that normal? Is that just what these tidal turbines do? There is historical data for tidal turbines, but when you start to apply those to different operating environments, and these turbines are the first ones at 1.5 megawatts, were what we're seeing very normal. And just to give you a comparison of that and some ideas of that. So because we have a tidal cycle, the turbines will typically sit idle for maybe 60 minutes, where everything cools down. As the tidal flow increases, so our generator temperature increases. So we can plot generator temperature against flow. The problem is, if we do that when the flow is decreasing, because the turbine's now been operating for a couple of hours and is warm, the temperatures you get from the generator on a decreasing flow are much higher than they are than when they're an increasing flow. So you have to start breaking up the data for the turbine to understand what was it doing prior to the value that you got, and actually, is that just normal? And you get a spread then across your generator and your generation. We've also been working through and picking out variations in performance. So if we look at our variations of springs and neaps, the picture bottom right shows you a capacity factor variation for some of the turbines that we get, and it's very different between a neap and a spring. So if we're looking at a month-on-month forecast, we have some availability loss during a spring period, our capacity factor drops. Now, is that just normal and the turbine's operating, or is there a different effect going on here? So there is an effect there that we have to unpick within the information that we get from the turbines themselves. And we also then look at what's caused the availability loss, and understanding, and there's a lot of concern around the availability of turbines. Certainly in the early years of the array, we actually found a greater loss of availability from the grid than we did from the turbines. The turbines were actually available. It was the grid that was giving us problems, but that's something outside our control. And then the onshore converters have also been have had their issues, which we've resolved and moved forwards. And we've had some issues with the switchgear as well. The switchgear has been caused by it being a tidal array. We wouldn't have seen it if we were a wind turbine. But again, it's just picking up that what's caused this and how do we understand to overcome it. Looking at the flow on site, and it's quite interesting listening to the previous conversation, previous presentation. So the turbines that we've got all use independent blade control. That's been standard since we started. And I think part of the difference you'll find in tidal turbines, and I saw one of the questions earlier on, that the operating environment for a tidal turbine is seen as being less onerous than wind. I would disagree. It's very different. The speed, our pitch speeds are considerably higher than wind. So we are pitching our blades during variable pitch operation at a much higher speed. So our cycles are much higher. We're also seeing a higher level of turbulence, and the loading is comparatively probably higher because our blades are smaller, but we're still seeing higher loading. And also the turbines don't seek. Once you set them in the slack tide to look in a certain direction, that's all they do. So we do know that as the flow increases and decreases, we get a different heading in general across the flow. But also we get a different heading at depth. So you get a vertical skew in the flow, which is picked up then. Of course, how do you account for that in the information that you're looking at and assessing? Does that matter? Does it have a significant impact upon the loading? Do we have to unpick that when we start looking at loading? And also that we have cases where we have an offset azimuth on the flow coming through the rotor. So where you would normally expect the highest flow to be at the surface, it's actually not. It's actually the highest flow is offset by about 20 degrees. So the entire rotor, where in tidal bladed, we may have assumed that the highest flow would be at the top. That's not the case. And it's that unbalanced effect then that we see in the loading that we get in the vibrations. So some of this is accounted for, that we can change the headings of the turbines. But there is a significant effect across the site. Different turbines see different effects. So when we start trying to compare one turbine to another, they're not in the same operating environment. So it's trying to unpick, well, this turbine is seeing something different, but does it matter? Is it appreciably different? We also look at turbulence. Turbulence is one of our biggest drivers, and these are plots of kinematic turbulence, kinematic energy. So this is a plot of the intensity, 4 plots. We've got January and June. The top is the ebb and the flood left and right, and then the bottom is the ebb and flood left and right. The plot on the left is showing where the turbulence is kind of coming into play with regards to flow speed. And then the plot on the right, the blue plot, is showing the intensity of the distribution of those events. So in January, we see significant amount of turbulence around the 2 meters per second in the ebb. In flood, we don't see quite as much. It's more broad across the entire range of the flow speed. And then in June, the intensity that we see in January disappears. It's a broader spread across the ebb, and we still pick up this kind of higher turbulence in the flood towards the higher flow speed. But again, it's not, when we look at the distribution plot, it's not as much. There isn't a huge amount of time spent there. But the variation in the turbine performance between January and June, when we see these different turbulence effects, can be around 5%. The turbines are doing exactly what they should do. But because the turbulence is such that the pitch system is trying to constantly seek to protect the turbine and catch up with the turbulence experiencing, we get this loss in performance. And again, it's kind of picking that up. When we start then looking at loading within the turbine, comparing loading in June to January isn't really appropriate, because the speed of variation of rotation and the speed of variation of pitch and the increase in forcings during January is significantly higher than June. So when trying to compare directly like for like, it's not always appropriate. This is something that we're picking up and understanding. I mentioned vibration monitoring. So that's a considerable number of sensors. Both have SKF systems across the turbine. We've had SKF in several times to sit down with us really and go through some of the data that we've got to help us understand what we're looking at and what we're seeing. There is currently no standard settings for limits or vibration sensing within tidal turbines. There is for wind, but we already know that actually the wind settings are not appropriate for tidal turbines. We can experience a 50% increase in our speed in about 2 seconds, which is again due to turbulence, which wind turbines just don't see. So it's something that the loading characteristics are very different to tidal turbines, and trying to pick through that information using traditional methods coming from wind turbines, we're finding to be fairly inappropriate. We are looking more towards automotive rather than offshore wind, because it is that acceleration and deceleration that is more pronounced in what we're seeing. We don't have any answers for this, by the way. This is still very much work in progress of understanding how we pick through this data. And moving towards a predictive maintenance, we can plot time series data. That's very simple for us. We can extract information month on month, week on week, year on year. And we can compare month on month, week on week. But again, it all falls back to, yes, I'm seeing a higher load here, I'm seeing a higher frequency, but was that caused by turbulence? Or do I have a problem, mechanical problem in the turbine? And trying to unpick that is actually is fairly difficult. Moving slightly away from the turbines themselves, looking more at the assets really that are laid on the seabed and not really moving a huge amount. The pictures bottom left is one of our submarine cables, just showing an area where the cable's sliding around on the seabed. And on the right hand side, this was not long after, about a year after installation, we've got a small nick in the outer armor. So every year we go back and we look at the cables, we look at the foundations, and we visually inspect them. And really, we're looking to understand whether they're moving and where they are moving. The cables were laid on the seabed, exposed bedrock. There is no sediment. It's a tidal array, so there is no sediment there at all. And our options for really secondary protection are limited. The cables are very heavy. They're quad armored. But our protection really is only 4-ton rock bags that we can place along the cable. So the picture bottom left, we would certainly place a rock bag in the proximity of that and stop that from sliding. But we are very aware that the options around that are limited. So we are working with Catapult, talking with Catapult, but we are discussing with Photech and some other companies around bringing in DAS systems to monitor cable motion with the view of that actually monitoring cable strain. So we know we had them on site actually this week to do a little bit of work with us, and we know we can hear the ROVs flying around the cables through the fiber optics, which is quite impressive. So we can hear the cables moving on the seabed, and then we can measure and monitor their effect of their motion during the tides. And it's really getting to that understanding of, okay, so the cables may be moving, but is that detrimental to the cable? Will it shorten its life, or is that motion acceptable? Which is a bank of information that we really need to pull together. And finally, we also wander around looking at the turbines, and we go around looking at the foundation. So the pictures on the right, the top one is during installation or just after installation. It's nice and clean. And then the bottom photograph is the foot last year with a collection of rocks around it, which have been pushed in place by the tide. So we know the seabed down there is fairly dynamic and rocks do move. It's understanding that does that give us a problem with regards to the flow around the foundations and just the other elements, and then looking at the turbines as well. Looking to the future for us now, where are we going with this? What are we up to? So Continuing to visually inspect the turbines. We'll do that in the assets every year, and trying to reach a position where our cable risk can be self-insured. That would be something that we are trying to, one of our objectives. Collecting data from the generating system, the whole turbine to grid, not just the turbine, but everything else. And really to develop a true foundation of robust asset management. So a real understanding of actually normality modeling, and then understanding if we are seeing something, what is that problem? Set up the rules that we can then understand that if we do see a higher temperature or a higher bearing frequency, what was that caused by, and should I be concerned? Still working on the flow around the turbines. We're still gathering information. It's interesting that even year on year, it changes slightly. And is that a problem? Is that outside the normality of what we would have seen? And then concluding a lot of that as we go into the first maintenance cycles in 2023. And then that gives us the opportunity to really dovetail, if we have the data from the condition monitoring of that, inspections of the turbines, the bearings. Do we see any concerns, and do we see any issues? And that is it for me. So thank you very much for your time. And I will pass over to Mikhail down at HydroQuest. Sorry, HydroQuest.
Yeah, thanks for the introduction, and good morning, everybody. So I will talk a little bit about our approach to reliability and condition monitoring. Just first, a few slides to remind who HydroQuest really is. Our company is based around the turbine concept, which is vertical axis bi-rotor turbine. This is a design that we think have competitive advantages that will help us to reach competitiveness in the tidal market. Just a reminder of where we come from. The company was founded in 2010 with the aim of going for the niche river turbine market. And in 2013, the first turbine was installed and connected to the grid in French Guiana. In 2014, our partner CMN, which is a French shipyard, entered our capital with the aim of adapting the technology to tidal turbines. This took the form of an ambitious R&D project that was launched in 2016 and what we call OceanQuest, with the aim of developing a 1 megawatt prototype tidal turbine. So this prototype was built in 2018 and 2019 and is currently generating electricity on the EDF test site of Paimpol-Bréhat. The markets, probably most of you know it, but as was said previously, there's a big market in France and UK, and then other sites around the world. So of course, we will aim for the French market first, because our production site in Cherbourg is right next to the Roi Blanchard. So this partnership with CMN really makes sense from financial and industrial point of view, because the shipyard is located right next to one of the biggest sites that we aim for, and it has the right capabilities for production. It's adequate in terms of size of turbines and the industrial equipment that they use for production and assembly of the turbines. So this is why we think this partnership makes a lot of sense. So talking about this prototype project, you can see the turbine here and what it looks like. So we see the bi-rotor vertical axis turbine, 280 tons dry weight, 250 tons for the foundation, ballasted with 1,000 tons of cast iron. The turbine was deployed in April 2019 by a DP vessel. It's achieved a high availability right from the beginning, about 91%. We had its power curve certified by Bureau Veritas at the end of last year, and we expect to decommission it next summer and take it back to the workshop for expertise and analysis. Our approach to reliability really starts from the concept. You can see the figure on the top right is the flow direction between flood and ebb tides. You can see that we have a fairly bidirectional flow, and which is in an equation with our turbine because it can operate in both directions up to 15 degrees of incidence without yawing the turbine. The vertical axis also allow us to work without pitching the blades. We complete this approach with having as little moving parts as we can. So no pitch, no yaw. So really the only moving part is the drivetrain, rotor, generator. We use direct drive generators, and conversion system is embedded in order to manage the variable speed. We try to focus our innovation effort on the design and comparison of this vertical axis rotor, which is we're still learning really how it works in a real condition flow. And for the rest, use industry standard components, for example, wind generators and converters. Our approach in design, in reliability by design in this first prototype project was to fulfill the following project objectives. So continuous operation during the test period, testing of our reliability strategy, and improving our knowledge base of operation conditions. This really echoed the previous presentation, where we're really trying to define what's normal operation conditions. So we tried to reach these objectives by having a reliability by design philosophy and a comprehensive monitoring system. Our design approach is that we have birotor turbines, so this is kind of a native redundancy that we try to make advantage of. And you can see the figure on the bottom is the energy repartition depending on the turbine operation point. So we can see that there's a fairly large part of the energy production that is made when the turbine operates at around 30% to 70% of the power capacity. So what we've been trying to do is to determine the right level of redundancy on the system in order to keep the cost down and allow maximization of the energy production by having a partial redundancy strategy, meaning and for this we define N-1 and N-2 criteria, and by that we mean what happens if we lose one of the major equipment. What will be the impact of losing this equipment until the next maintenance cycle? So this is where it's important to see that the energy repartition is also good when we can't operate at full power. So this allows us to maintain high energy production even with a partially operating system. So these allow us to have a statistic approach and to integrate this approach in the production calculation, so we can have a reliable energy production forecasts. we complete this approach with the most comprehensive condition monitoring system that we can. So we monitor vibrations and loads in order to define mostly the fatigue component and the mechanical part, and also monitor the ambient temperature and temperature rise in the power system components, because this is a major driver in their life expectations. So this is also coupled with ADCP measurements to link all these operation parameters to the sea state and current speed. So we know, again, like was said in the previous presentation, we're trying to define what's normal conditions depending on flow, sea state, turbulence, and current speed. For the next generation of turbine that you can see here, so its concept is still here, bi-rotor vertical axis. Turbine is bigger, it's lighter, and it's going to be more powerful. We're trying to keep the same approach, but the project objectives are different, of course, because we are reaching for a commercial project with 20 years service time. We aim for very high availability, superior to 95%. We, of course, need accurate energy calculation, P90, P50, for be able to set up a business plan. And we, of course, we want to keep the maintenance cost down, which means having the highest possible maintenance-free spans. So we are quite happy with the result of the philosophy we've used on the prototype project. So we will keep this approach. We will have stronger N-1, N-2 criteria. We'll still have quite comprehensive condition monitoring with the aim of moving toward predictive maintenance. And of course, we've used the measurement of the prototype to update our numerical analysis tools that can define the mechanical loads and stress, as well as the operation condition for the power system. With we fed the real measured data in this model, so we can have a better model and a better understanding of how our next generation of turbine will operate. So that was it. Just a reminder of the main points we're trying to. We've approached reliability right in the definition of the turbine concept, and we're trying to decline that in the design. So we've reduced the number of moving parts to the bare minimum. We implement partial redundancy strategies to optimize the cost of the drivetrain and try to make use of the native redundancy of our concept. Having comprehensive condition monitoring system is key in order to understand the operation conditions and move toward predictive maintenance. The aim of this is, of course, to go towards cost reduction. There is an optimum to be found between the global CapEx and OpEx costs. It's the challenge is to find the good level of redundancy to optimize the global CapEx and OpEx costs and achieve high availability, lowering the maintenance costs, and of course, having a reliable statistic approach to energy production calculations. So that was it for my presentation. And next speaker is Stephen Robertson, which is Head of Business Development at the RE Catapult.
Hi everyone, can everyone see that? Hello?
Yeah, that's perfect, Stephen.
Yeah, we're okay, we're good to go?
Yeah, thank you.
Okay. Good afternoon, everyone. My name's Steve Robertson, and I work for the Offshore Renewable Energy Catapult, and I'm head of business development for the Blythe site, which is the main operational test centre. So what I'm going to do today is just give you a very brief overview of the test facilities and their operation. We've been involved in the development of tidal energy since the inception, and I'd like to give you just a brief overview of how we've approached the reliability of tidal turbines. And I think Fraser will see some very familiar pictures. It's very visual. Sorry, I'm just trying to. Looks like I've lost my. That's it. Okay. So very brief agenda. I'll try and keep it brief. Welcome to Offshore Renewable Energy Catapult Blythe site. I've got a very a quick overview of the site itself. There's some obvious questions that we've been asking today, which is why test prior to deployment. So I've got some views on that, which I'm sure will generate some questions and so on and so forth, comments, and then an overview of the 1 megawatt and the 3 megawatt test rig, which are the ones that are predominantly used for testing of tidal turbines. Since the operational start of the test rigs, we've tested 5 tidal turbines, and I've got some pictures of the ones that we've tested, so it should give you an indication of our experience in that field. And then the Q&A, which I think Tia will take over. So the Blythe site, it's based up in the northeast of UK. We are part of the Catapult structure, so we are supporting everyone in the UK or actually internationally with any testing needs, and we're involved obviously in the Tiger project. So all of these facilities, albeit the tidal ones will be the most important and the most interesting, will be available to use as part of the project. So as you can see, it's quite a comprehensive and a concentrated site. We've got a lot of offshore wind blade testing capability. We've got a 100-meter blade test facility there, which is at the moment just completing test of a 107-meter offshore wind turbine blade. We've got a 15 megawatt powertrain test facility, which houses the GE Haliade X at the moment. And that's a 12 megawatt stroke 13 megawatt offshore wind turbine. One of the main tidal turbine test facilities is in the 3 megawatt powertrain test facility, which is built into the top end of one of the dry docks. And then we've got also the Disruptive Innovation Test Center, which is effectively a smaller blade test facility, but we're also housing the 1 megawatt powertrain test facility in there as well. That combined with the subsea facilities we have, so we've got dry docks, wet docks. We can test a lot of ROVs, cable. We've got an artificial seabed, so we can test trenching and cable burial sensoring systems and so on and so forth. And then also we have quite a large high voltage lab, which does a lot of cable testing and anything to do with things like lightning tests and so on and so forth. And we have an offshore wind turbine training tower. We do have some offshore test sites. We have an offshore wind test mast, MET mast, which actually is wind and wave measurement off the coast of Blythe. And we also have a 11-mouth turbine, which is is the turbine that Hyunju was referring to with regards to the condition monitoring. So why would we test prior to deployment? I think we've come to the conclusion, which we would, obviously, that onshore testing gives you a huge insight into what can happen when deployed. And I think we've been proven, that has been proven with regards to the recent experiences that we've had with the tidal turbine manufacturers, and also I think with some of the validation of models and so on and so forth. So proving performance curves. A lot of this is obvious and it's not necessarily anything new to anyone, but it does just give you an insight as to what we are capable of doing. I mean, these two rigs are actually, they're designed for pretty much tidal turbine development. So we've nailed our flag to the mast and so on and so forth with regards to helping the industry to bring forward the innovation. So accelerating innovation, the design and materials, addressing unknown scenarios. We found that out that with one of the extended tests that we carried out, that whilst the major concern was around the gearbox, the main areas to address were the power conversion areas. So there's lots of evidence of those sort of things developing and coming to light. Validating models, assessing turbine reactions to faults in pitching, increased load, bending moments, which obviously links into Fraser's and Hyunju's presentations. What we have also done, which is what Fraser has touched on, is grid compliance. So the 3 megawatt rig will actually have a mini e-grid connected to it, so we can monitor and we can feed in the conditions of grid, dropouts, low voltages, that kind of thing, black starts, into the 3 megawatt test rig, which will be a huge bonus to the rig. It becomes a fully compliant test rig rather than just a mechanical test rig. So I've got a couple of videos which I'm not sure whether is probably going to take us over the time a little bit. What I might do is play one of them, if it's okay with you. This is the video that actually is the timeline of the building of the AR 1500. So it's quite relevant to Fraser's presentation. So if let me see if I can get this to play. It's only 3 minutes. Okay, so I hope that was quite insightful and not too long. We did try and speed that up, but so whilst we approached and we addressed the large scale tidal turbines of the day, we also realized that when semi-submersible tidal turbines came along, it was really important to try and address the smaller scale turbines, and this is where we then developed the 1 megawatt test facility, or the sub 1 megawatt test facility, of which a company called Turbines were quite instrumental in that, because it was a joint funded project. And we tested their T2 tidal turbine in a wet environment, which again was a good learning curve for us, and I think also for Turbines. And we've also discussed the CIMIC Atlantis turbine should really be just Atlantis, then to be CIMIC, but it was 1.5 megawatt wind tidal turbine, of which Fraser has already alluded to, which is the one up at Pentland Firth. And then from that, we've developed a couple of other projects. One which is the tidal, the Nova Innovation D2T2 turbine, which we've actually tested recently. We've got quite a good relationship with Nova at the moment, where we have a funded project in Fay, and then also they're coming back to do some controls measurement testing through Element, which is another project that we'll be embarking on. So that the pipeline for that small sub 1 megawatt tidal turbine test facility is really quite compelling. We have a long pipeline for that, and also we are looking to make enhancements to it. At the moment, it's a torque drive only, so we have no non-torque loading capability, which we have with the 3 megawatt rig, which I think probably take a little bit longer to go into discussing that, but this is something that we're looking at, and we're also looking at putting in a mini E-grid into the 1 megawatt tidal, the 1 megawatt rig facility as well. We also tested the MCT Siemens tidal turbine, which again is now part of the CIMIC Atlantis portfolio. We actually tested that over a period of a year, and of which 9 months of it was robust fatigue testing, in which we estimated and we calculated that we'd given it 18 years of wear within the 9 months. So that was an accelerated test program, which they found was absolutely critical to the development of the turbine life cycle. Then also we still use the rig for component testing as well. So we've got some novel generators that have been tested on and are coming back to test. So what it means is that we're not just there to test full systems. We can test components as well. So on this slide, you've got a ferrous magnet generator, so removing the need for the special magnets that we would normally use, and then also we have a novel magnetic generator on the other side. So very flexible test rig, going to be used a lot. And then just very briefly, just to finish off, realizing it's 12:20 and the webinar finishes at 12:30. This is just some pictures of the other facilities, and obviously with regards to the other research programs that we're actually working on as well. So yes, so that's what I wanted to get to, where we have Wind Blade Research Hub. So I know it's a bit rushed and a bit on the manic side, but hopefully that'll give you a brief introduction to the test facilities at the ORE Catapult. So I'll hand back to you, Theo. Hope that was quick enough for you.
Yeah, thank you very much, Stephen, and sorry to have to prod you to speed up there.
That's fine.
We no have slightly overrun, and I just wanted to make sure we had enough time to go through some of the Q&A questions. So one of the questions I think was aimed at Hyunju during your presentation was that you identified that discrepancy between the model and real life, you know, of approximately 10%. Are there plans to update the model to reflect that difference?
Yes. So actually, I hope to mention two things. One is the very common and most accurate the loading calculation software doesn't include that level of detail for the controller. So even though we adjust the existing controller, it cannot resemble exactly what happened in the field. So again, in globally, you can have some level of accuracy in terms of the wind speed and the output of the generator and some the overall structural loading. But for certain component here, such as a pitch or main shaft bearing, the difference can be huge between the calculation and the real field. And the other one is the issue we hope to raise is the design calculation can be done in early stage of development and cannot be evaluated until the prototype test actively started from in the field. So as you can imagine, after you complete detailed design calculation for the component load, you will use that load calculation result to select a design of kind of the sub-component of wind turbine or tidal turbine, but still you can consider that can be quite differ from the real field. So it should be evaluated. So that is a 2 point I hope to raise. Thank you.
Yeah, thank you, Hyunju. I've got another sort of open question to both Fraser and Mikhail, and sort of having seen your presentations, it's clear that some of the models that we use to predict our tidal sites and the environmental conditions there, there's still room for improvement with them, and particularly when looking at sort of micro siting turbines and the individual environmental conditions they incur. I just wondered, are SIMEC and are HydroQuest sort of looking to learn from well, operational data that they're collecting to improve those models? And is there a sort of secular sort of methodology for learning from them? And then a secondary question, obviously offshore wind have already deployed large arrays offshore, and are there learnings that we can make from what they've done and what they are doing? And is that something being considered by HydroQuest and SIMEC? Fraser or Mikhail?
Okay. So, not wanting to answer for the turbine designers, but knowing what I know around their model. So, they use tidal bladed, and we know that tidal bladed is conservative. Tidal bladed is an extension of bladed, which was used for the offshore wind industry. We know its limitations, and both turbine suppliers have calibrated tidal bladed against their operational data. At the moment, I'm not aware of any interest in the supplier of tidal bladed to do any work on it, to make it better, to make it more accurate. We know that it doesn't work very well with turbulence, but there is a way. We understand how to overcome that, and we understand what the impact of loading from turbulence is on the system with regards to extremes and means. I think for that perspective, you're always going to have an element of that within any model that you use, that it's not going to be perfect, but you need to understand where it's wrong and where it may be accurate. Within the guidance and within the insurance that we use at the moment for designing the systems, we, as close as possible, continue to comply with DNV, which requires that we need to use a validated design package. And as there is only one, that's really all we can use. So I don't see anything changing much in the next 4 or 5 years. We need more turbines in the water for more interest to really come from bladed to do any work on that system.
Thanks, Fraser. Mikhail, have you got a response?
Yeah, I mean, what we've been doing is that we've tried to record as precisely as we can the operation condition with the ADCP measurements, and then we went back to our simulation before the deployment of the prototype, and we looked at what we expected in terms of loading related to current flow and turbulence and everything, and then we used the measured data to optimize the simulation tools that we have to improve it to the point that they would have been 100% predictive on the prototype. And then with DCP measurements of the future deployment sites, we think that our simulation tools will be predictive enough to have realistic operation conditions and design criteria.
Thanks, Mikhail. And I've just got time for one very quick question, and it's within the offshore wind industry, there's a big drive for automation and autonomous systems for maintenance and surveying. Do you think that's a trend that tidal will follow, or are the challenges quite different and perhaps slightly too challenging at this stage?
I think, Teo, just from a site survey perspective of going out and checking the assets, I've already run a survey from this desk with an ROV subsea, transmitting the data over a live feed, so I can watch it almost real time. It's half a second slow. So I think you could do that. You could certainly, it's completely feasible to have an ROV working remotely. We're doing it with forklifts, so why not do it with ROVs? It would just be the benefit, it would very local to the turbine. So you could get around the turbine and have a look, but you probably wouldn't get able to get down the cables. And affecting maintenance, really, the turbines have to be designed and developed and built such that they do not need recovery. They have to be so robust that they are bulletproof. And that is the big challenge, making sure that they have limited systems, and the failure of one little light bulb doesn't put the system out of operation. That's the challenge. So I don't see a massive benefit for remote equipment outside the turbine.
Thanks, Fraser. Mikhail, have you got anything to add very quickly to that? Appreciate it.
No, I really agree with what was just said. I mean, there's accessibility issues that make automation very difficult, and we have the same approach that, as I said, we use redundancy, maybe partial redundancy, but as was said, we should be able to afford the loss of an equipment without having to recover the turbine. That's also our approach.
Okay. Right, I'm afraid we've run out of time. So just to finish up, so I'd just like to quickly plug the very final of our Tiger webinars for Series 1. That's this coming Friday, and its theme is offshore and onshore mobilization and logistics. And we've got speakers from Monesto, Sabella, James Fisher, and Dublin Offshore on that webinar. So if you are interested, please go to our Tiger website to register for that one. So just quickly to say thank you very much to all of the attendees, also to all the speakers. Thank you very much for your presentations. Just a quick mention again for our co-host, Oceansgate Plymouth. Thank you very much for co-hosting this webinar. So thank you very much, and hope to see you in our future webinars. Thank you very much.
Cheers, Teo.
Thanks. Cheers, everyone.
Thank you. Bye-bye.
Thank you.